What's up mga ka-axis? In this video, I'll be discussing the process of calculating the Jacobian matrix of a Cartesian manipulator. What is a Jacobian matrix? Jacobian matrix is a fundamental concept in mathematics and physics. It is a matrix of all first-order partial derivatives of a vector-valued function. The Jacobian matrix plays a crucial role in the study of multivariable calculus, optimization, and differential equations. Understanding the Jacobian matrix allows us to analyze the behavior of functions in multiple dimensions and helps in solving complex problems in various fields of engineering, economics, and computer science. The matrix that relates the end effector velocities to joint velocities is a Jacobian matrix. Constant velocity or displacement over time is represented as V is equals to d over t. Average velocity is the change in displacement over change in time, represented as V is equals to d sub 2 minus d sub 1 over t sub 2 minus t sub 1, or V is equals to change in displacement over change in time. Instantaneous velocity is the rate of change in displacement with respect to time, represented as V is equals to dd over dt, or V is equals to d prime. In this topic, we will use instantaneous velocity for Jacobian matrix. So these are the types of velocities that we need in order to get the Jacobian matrix. First is velocity is equals to d of d over d of t. Angular velocity represented as theta, the angular displacement, or d of theta over d of t is equals to theta prime. Linear velocity or x is the linear displacement, or the d of x over dt, represented as x prime, y prime, z prime, and the d prime. Angular velocity is for rotation, and linear velocity is for prismatic. This is the general formula of Jacobian matrix. X prime, y prime, and z prime is the linear velocities of EE at x, y, z direction, and omega x, omega y, and omega z is the angular velocities of EE at XYZ axis. The concept of the Jacobian matrix was first introduced by the mathematician Carl Gustav Jacob Jacobi in the 19th century. But now we are going to obtain the Jacobian matrix of a Cartesian manipulator. But first, we need to know the dimension of our Jacobian matrix. For the columns, it depends on the number of rows in DH parametric table of our Cartesian manipulator. Our parametric table was 4 rows, therefore, our column in our Jacobian matrix is also 4. Now, after knowing the dimensions of our Jacobian matrix, let us get the elements inside of it. Let us try to get the end effector velocity vector, the Jacobian matrix, and the joint velocity vector. Jacobian matrix of a Cartesian manipulator. So this is our Cartesian manipulator. There are a lot of methods in obtaining the Jacobian matrix. First one is partial derivative method, second is propagation method, and etc. But we will use the linear algebra method. This is our linear algebra method, wherein R is represented as the rotational matrix, D is the positive vector, F which joint is being solved, and N is the number of joint. Our Cartesian manipulator is composed of prismatic joints. Only that is why we are going to use the formula of linear and prismatic only. First, let us incorporate the formulas for linear and rotational part. Then, solving the column 1 of the Jacobian matrix, which is the stand. So what we have here is an identity matrix or the stationary matrix. Why? Because it is a stand, it doesn't move. We will multiply the identity matrix to the formula. Then, solving for the column 2 of Jacobian matrix. For the second column, we will get the rotational matrix of RO1 and then multiply it to the formula. For the third column, we will get the rotational matrix of R02, but there is no R02 in our computation before. So in order to get that, we will get the R01 and the R12 and then multiply it to get R02 and then multiply the R02 to the formula. Now, solving for the column 4 of the Jacobian matrix. For the last column, we will get the rotational matrix of R03, but because there is no R03 in our calculation before, we will get the R01 and the R12 and R13 and then multiply them and then multiply the R03 to the formula. After that, we will be substituting the matrices of column 1, 2, and 3 to the Jacobian matrix. This is the Jacobian matrix of our Cartesian manipulator. And then we will multiply our 6x4 Jacobian matrix to our 3x1 joint velocity vector and obtain the differential equations by equating them to our end effector velocity vector. The first column is the stand, so we are gonna keep it as it is. Then this is our differential equations. I hope you understand how to solve the Jacobian matrix of a Cartesian manipulator, and that is all for this video. Thank you so much mga ka-axis.